Okay, so in the last video, we did an example problem, and what we did was a Gilman reagent, and we had this alkyl halide, and we reacted it with a Gilman, and we made a product, and we said this is the product, and we showed how complicated that whole process was, right? So we need to do some more examples. That way you can feel even better about these examples as I go forward. All right, so here we're going to do a ring, and this ring is going to have a circle in it, which means that this is an alternating double, single, double cause me trouble bond. So double, single, double all the way around. It is a very delocalized system, and delocalized means that the electrons can move. All right, so off of this, I'm going to put an iodine on here. We just need a halogen. We did bromine last time, so why not change it up and do iodine here? And we can. We can do chlorine as well. Again, the only thing we don't like to handle with is fluorine because those are very explosive. So we leave those off and we don't fool with them. But chlorine and bromine and iodine, they all do the same thing, folks. There's no difference. All right, so we're going to react this with a Gilman. So this time we're going to choose a different type of Gilman. Let's do a CH2 double bond CH. All right, and we're going to pair those up, and we react that with our Gilman. That is our Gilman reagent. So you're looking at this and you're saying, oh gosh, you know, there's got to be a trick, right? I mean, he's showing me this example because there's going to be some kind of issue, some kind of monkey wrench that gets thrown into this thing. I've got this ring system that's delocalized. I've got this R group, but we've just did really ethyl groups and methyl groups. We haven't really seen something that has a double bond in it like this. So what's the trick? What's up your sleeve? All right, so let me show you. So just like before, I always start with my reagent, and my reagent is here, and there's the iodine. And like before, we target the halogen, and we go with our mouth. There you go. If you make the noise, it helps. It makes you understand it a little bit better. All right, so we get rid of the halogen group, and what goes on is a coupling reagent, and that couple is the R group that's on the inside, and you would have said, well, CH double bond CH2. That's kind of what goes there, right? The side of addition is always on this side because that's my nucleophile, and this carbon is my partial positive carbon, and that halogen is electron greedy, so that's partial negative, and that halogen takes all the money away from that carbon, and that halogen gets greedy, and that carbon says, hit the curb, I found somebody better than you, now leave me alone because you're ugly too. So iodine goes off, and this carbon goes on instead. So this is what you would have predicted for the Gilman because you have used the same template that we used for our other two examples. And if you did this, you're correct. There is no difference. It shouldn't be a difference, right? I mean, very few times do we get these little kinky things that happen that I would not predict. These little weird things that go on. But folks, just because it's a ring system that's delocalized doesn't change anything. And just because this is a double bond in the Gilman, that doesn't change anything either. Both of these are perfectly fine. So this is the product that gets formed from this reaction. Now, if you want to talk about the other products, we can review that. I mean, I will never ask these on a test or anything, but it's probably good to understand that you still have one of these pieces that's out there that is paired up to the copper. And it's also good to understand that that lithium is going to break apart, break away from the copper. It doesn't need it anymore, and that will pair up with the iodine that was spit off by that benzene ring. So these are some of the byproducts that begin to form from the reaction. So they're going to be in there. They need to be cleaned up. But folks, this is my major organic product right there. That's all that there is to it. So one of the weird things that happens here is that these reagents, the Gilman, we can react them with things like aryl halides. These have been problematic before in the past, especially in substitution land. All right, and the reason is because in substitution land, right, let's say that we have an OH group. That's a nucleophile. That nucleophile is going to come on into the carbon, and right there it is. But this benzene ring is surrounded by electrons that can move throughout the ring, and it just constantly pushes those electrons away. And if something's negative, it's going to push that negative away. So these were very hard to substitute, and that was the reason that we never really did anything with them. If you noticed, everything that we did in substitution land was like primary and secondary and tertiary things. We rarely ever did aryls, and that's because they can't really undergo a substitution. So the question is, how on earth can I get a halogen like this off and replace it with something else? Well, substitution's not going to help us out here because it can't get in order to substitute for anything. So this is a problem for us. We can't really have this happen. Vinlics were also a problem as well, and that's what this particular carbon is. That is a Vinlic carbon. Remember, Vinlic is a carbon double bond carbon, so this is a Vinlic carbon. If we had a carbon double bond carbon on a carbon, then this is the allylic carbon. These were all from Orgo 1. So Vinlics were also an issue because with Vinlics, we saw this double bond that was right there beside of that carbon. This carbon just so happens to be negative. How on earth can that negative carbon be there with a double bond that's right beside of it? And we just stayed away from Vinlics most of the time in Orgo 1. And this was one of the reasons. They just did not react like all the others reacted. So aryls and Vinlics were always a problem for us. But not here. Gilman is perfectly okay with these. And as you saw here in this example, it can easily take an aryl and a Vinlic and slap them together and say, here's your product, baby. And that's exactly what we got from this reaction. All right. Okay, so let's take a look at another example. Let's keep working. We feel really good about these, I hope. So we'll just keep doing things and we'll see how far we can get with this. So let's take CH3. Off of this is a CH. CH3. I've changed my mind. Let me do a CH2 here and a Br that hangs off of there. Got to have a halide or this can't work, right? So carbon double bond O with a CH3 group. And let's add a Gilman to this, CH3, and we'll just keep it simple. 2, copper, lithium. All right, so the magic recipe of Gilman says, you take an alkyl halide. Well, I do. I have one. I have a R group with a halogen on it. My halogen's bromine, and the R group, that big blobby thing there. And then it says you add your Gilman reagent, and I do. I have a Gilman reagent. Right there it is, copper lithium, and that's paired up to 2 methyl groups. And these two things come together and they make a reaction. Okay, so the issue here is that this is a more complicated type of molecule, and that complicated type of molecule has other things in it. And this is a C double bond O. All right, so how do we handle this type of situation with Gilman? All right, so let me show you how to do this. I'm going to rewrite it. Br, CH2, CH, CH3, carbon, double bond O, CH3. All right, so there's that. So Gilman says, and I'm going to do as Gilman does. Gilman says, take the halogen and get rid of it. And then replace that with the R group that's in parentheses. That's it. That's all. Gilmans are very friendly. Gilmans are very easy to figure out what to do with. As long as I have an alkyl halide. then these things are going to work out for me very, very well. So one of the things that I will say here, though, is that in all of these examples, we have chosen copper lithiums that are on R groups, and we have chosen these halogens that are on a different R group, right? They don't have to be the same, meaning that this was a methyl. This did not have to be a methyl bromide for this reaction to happen, okay? Or in other words, here is the halogen. I do not need this R group in the Gilman to basically be the R group that matches here. I don't need that. They can be completely different. It doesn't matter. But if you go back and take a look at some of our examples that we've been doing, we are staying away from secondary and tertiary versions. They just don't work out very well. So because of that, we just don't bring them up that often. We don't put them into our example problems. But a full-blown secondary and a full-blown tertiary, folks, it's just not going to work out very well. Now, if they're on double bond carbons, well, they're Vinlic now. It's not really secondary anymore, okay? These are Vinlic carbons that they are on. Those are okay. But a full-blown secondary and a full-blown tertiary, we just don't use them that often with a Gilman. All the other carbocations that we might have in these kinds of things will work completely fine. The aryls and the Vinlics, all of that stuff we've talked about before already. But we do stay away from some of these, and those are some that we do stay away from. Now, I will say that they work. They just don't work out very well. And out of these secondaries and tertiaries, the secondaries and the tertiaries, folks, the secondaries will work more than the tertiaries, of course. It's easier for those alkenes to get in there and go to a secondary spot. But tertiaries are going to be a little bit more stubborn, and we just don't really like to talk about them. Again, the mechanism's not fully understood, so we can't go into detail with some of these things. I'm just kind of telling you what the habit is as far as the textbook goes, or as Blackboard goes, or maybe Mastering Chemistry if you're on that software platform. So let's take a look at another example. Let's just kind of work through it and see if anything changes. All right, so CH3, and then we have CH with a Br that hangs down like this, and then a carbon double bond O and a CH3. And they want me to react this with, let's keep it the same, CH32 CuLi. All right. Well, my solvents like THF or ether, I'm leaving those off of all of the examples, but they're there. THF and ether is the jacuzzi tub that allows these things to come together to make a product. So if I look at the halogen here, my bromine, that is onto a carbon, and this carbon is a secondary carbon, right? There's one to the left and one to the right. Well, they don't really like to do this. They can be somewhat stubborn, but we are going to draw a product for this, all right? So this product is going to be CH3, CH, down here below, Br, carbon, double bond, CH3. Very similar to the last one that we did, but it's not the same. Or is it? You tell me. And we're going to add on this methyl group. So we go, there we go, and we add on our CH3 group. So we're going to go ahead and write that down. We're going to say this is the product for this Gilman reagent, or this Gilman reaction. Once more, we try to stay away from those when we can, but they can happen and they can go forward. We're just a little uneasy with them. All right, next. Let's do another. Let's do a cyclopentane ring and a CH3 group and maybe a chlorine that goes here. And our Gilman. So copper lithium. I know there's got to bring in 2 R groups. What kind of R groups do we want to bring in? Let me just make it a little ugly. Let's do CH3, carbon, CH3, And let's make it even uglier. Let's put a double bond there and change this to a CH2. There we go. All right. So we have an organic. We have a Gilman. These two things react. What do we get? Okay. Tracy's not going to trick me. Here's my cyclopentane ring. There's the chlorine. There's the methyl group. So he wants me to react this with a Gilman. We can do this. I target my halogen. There it goes. And then I add on the R group. And that R group needs to be added on right there with that carbon. All right, so there's the carbon. And off of that carbon is a CH3 group that kind of points up. So I'll keep that same notation there. And that carbon has a double bond, so I'll keep that double bond there. And that goes to a CH2 group. There you go. That's it. There's your Gilman. All right, well, those don't seem too overly complicated, I hope. Hope you're okay with those. And then when you feel okay with those, you're then going to see an example like this. Describe 2 ways to make ethyl cyclopentane using a Gilman. They flipped the script. They reworded this type of question because we've been so trained of looking at reagents and replacing things, and now they give me a word problem, and they don't give me any structures. And then in addition to that, they're telling me what I've made, and they want to know, what did you use to get there? It's like a retrosynthesis problem. These should not be any more complicated as long as you know how to draw the product. So that means if you cannot go from ethyl cyclopentane to a structure, then you might as well say sayonara, because you're not going to be able to answer this question. They are assuming, and I am assuming, that you paid attention to Orgo 1 and you know how to draw these structures when they ask you to draw these structures. So cyclopentane is a 5-carbon ring. There we are. And ethyl has to come off of this. So there's 1 carbon and 2 carbons right there. So they want to know, this is what you're ended up with. How can you make it? 2 ways. Just 2 ways. Just give me 2 ways of how you can make this thing. Okay, well, think of Gilman. Gilman is a requirement, so you need this copper lithium thing, and you need to come up with some type of alkyl group to go on the inside of this. And that alkyl group has to be reacted with some type of halogen in order for this to work. So what do you actually end up with? What 2 pieces are you going to put together in order to give me that product that sits down below? So I'm going to redraw that product up here, just so we don't lose it, because I'm getting ready to erase down here so that we've got some room to answer this thing with. Okay, so there's a number of different answers that you could look at here. Let's say this ethyl piece here, there's our 2 pieces. Let's say it was as easy as that. I don't want to break up my ring, right? I don't want to break the ring up. I want to keep that as cyclopentane. If I'm given that choice, it's the easiest thing to do. So right there is the cleavage point. All right, so if that's the cleavage point, then, okay, what 2 pieces do I need? Well, I could, if I wanted, to take my left-hand piece, which is the cyclopentane, and off of this cyclopentane, maybe that's my bromo group that I want to bring in. Right? Is that okay? And then on the Gilman, let's say that this alkyl group here is what I want to add on. So I want to replace this bromine, and I want to add on 2 carbons right there. So CH3, CH2, 2. Can that happen? Well, okay, here's our bromo group, and that bromo is on a secondary carbon. It's not ideal, but it could work. I would give you credit for this. Are there better scenarios out there? The answer is yeah. And you probably will know that because guess what, folks? It says describe 2 ways to make it. So this is not the only thing that we can do in order for this to go forward. So let's kind of flip the script a little bit. Notice that I took my cyclopentane ring, and my cyclopentane ring is the one that I chose to put the bromo on. Okay, well, what if I flip it? What if instead I did a CH3CH2 and put my bromine there? Right? Instead of on the ring, I put it on the 2 carbons. I mean, that's an option. So that means that with my Gilman, I would need a cyclopentane ring, and I would need 2 of those. Okay, that's not really ideal either. You can see how kind of weirded out all of this gets. I mean, there's like a strange little pentane ring right there with just a hanging off carbon. I know, it looks kind of funny. Up above, we have this bromo group that's on a carbon, that carbon secondary. I know that's kind of funny too. We said we don't really prefer that if we can get away with it. So maybe that's not really the best way that I can cleave that bond to make these products. So there is another option that I can do from the very beginning. I can get rid of that cleavage site right there. And folks, I can cleave it here instead. I mean, no one says that I can't, right? I can do whatever I want to do. It just says describe 2 ways that I can make this. So I can make these bonds kind of break wherever I want them to break as long as this makes sense and as long as there's just not tricky things that are involved there that I need to watch out for. And this is going to be a better option for me. And the reason is because when I go in with my alkyl halide now, here is my ring, my cyclopentane ring, and there's the carbon that's off of that ring, so there's a CH2 group. I can put my bromo on that carbon. And look at what we've done by doing that. This halide is now on a carbon that is primary. And we know for sure these are good, right? Secondaries, tertiaries, we stay away from those when we can. But here now I've made a primary, and this makes this Gilman reaction happen much, much better. And then what we do with our Gilman, here's my copper lithium, and whatever we choose, we need 2 of those. Well, what do I need to add? I need to add that piece right there, and that piece is a methyl group, and this is a CH3. Again, it's primary. Perfectly okay with that. It's not going to have an issue. Right there, folks, there's an option for us to use, and that's a very good option. Well, just like before, I can flip this, right? I can flip it. So I put the halogen on the cyclopentane ring with the carbon hanging off of it. So let me just do the other half. That was a CH3 group. Let's put our bromine there. That's perfectly okay. Not a big deal. And then we'll still add on our Gilman, and we'll still bring in our parentheses like this. And this is going to require the other half. So here is my cyclopentane ring, and off of this cyclopentane ring, I'm going to have another carbon, that's CH2, and there we go. That's all it takes. All right, so I'm going to draw this maybe a little bit better. Cyclopentane with a CH2. So there's 2 options. There's 2 ways to make ethyl cyclopentane using a Gilman. We actually went through 4, but the first 2 were just a little weirded out on us because they were secondary based. And here I have a halogen that is primary based. Here I have a halogen that is primary based. And then my Gilman on this side, that is a primary carbon pretty much right there. And then this one is also a primary carbon that is directly attached to. So this would happen much, much better than the first 2 choices that we kind of spit it out and put on a sheet of paper. All right, so there's option number 1 up on top, and there's option number 2 down here at the bottom. Again, we cut it in half. We figure out what pieces need to be coupled together, and folks, we have it after that moment. All right, so let's take a look at another example problem. Here we go. It says, what bromo substituted compound is required to react with that Gilman that they've drawn for you in order to form the following compound? And that's where I'm going to stop this video. All right, so write this down. Try to take a stab at this. See what you can come up with. And then in the next video, we'll check your answer. We'll see if you actually did it the right way or not. So they're giving you the Gilman in this case. You've got to use this Gilman piece. So what type of halogen would you need to bring to the table in order to form the product that they're showing you on the screen? So go try it. Think through it. It's not very difficult. You just got to figure out the trick and then come back and push play on the next video, and that's where we'll pick up. So I'll see you then.